Okay, so I'm going to try and put some of the heating and hot water system that I'm installing in context by just quickly talking through the plan of the system and how it's going to work. So the thing that we've already settled on is the pellet stove. Now these essentially burn like a standardized wooden pellet. And in theory, this is pretty sustainable. Like in theory, they grow these trees in Sweden, and they plant as many as they cut down, and so the whole thing is carbon neutral. But in principle, it looks something like this. So inside here, you put your wood or coal or pellets or whatever, and then around the edge here, there's some kind of like water jacket, inside the metal structure. And as all of the heat is generated from your fuel here, it's heating up this water. So, maybe it's like sort of blue and it's cold here at the bottom. But as it moves through the stove, it heats up and it gets a bit warmer. That's not going to work. It heats up and it gets a bit warmer. So we end up with like a hot water at the top of the stove. Now the theory behind this is pretty simple. You can burn anything. You can burn wood, logs or coal, but there's a pellet modification. And what that looks like is there's just a little tray that sits inside here. And you have a tube that feeds in your pellets into the tray. And these are kind of dosed depending on how much demand there is for fuel. The pellets kind of sit in the bottom here. And there's also a fan. And this sucks air in, blows them into the pellets, and then forces the exhaust gases up the chimney as well. And then normally you'd situate this in your basement or something. This would run out to the outside, little rain cap. And this is what I'm doing in the room at the moment. So as for the pellet supply itself, it's pretty simple again. Essentially you have, R1 is about the same size as the actual stove. In the bottom there's a little funnel area. And on the top there's a motor. And the motor has this big shaft coming out of it. And there's a Archimedes screw there. It's inside a tube. So you fill the whole thing with pellets. They're like around here. And then when you want some more fuel, this turns. These pellets get dragged up inside the Archimedes screw here. And then there's some box which directs them into here. They roll down, they fall on here. And there is also actually an electric heating element underneath to get it started. So when it's completely cold, this heats up the pellets red hot. The fan is blowing on them. Eventually they catch a light. And then you just keep turning this motor and dosing the pellets in. So then you've got your supply of hot water. Essentially you put cold water in the bottom here. And then you take hot water from the top there, pump it in here, goes through, heats up, comes out there. So we have two kind of functions for this hot water. First, we want to heat the house, and then secondly, we also want to be able to use it for showers, and the taps and washing up and things like that. So let's draw the house over here. I'm just going to draw a simplified model of the house here. So let's say we're going to include a hallway, and we're going to include one big room and then another room here. So the way that in most houses, what you do is you'd put a radiator in each room, you'd plumb the hot water to it, and you'd heat it up like that. But cleaning behind radiators is dusty, and they actually take up quite a lot of space on the wall. So a more modern thing to do is to put in, let's draw the room in sort of pseudo 3D here. Another thing you could do is you could put in like an underfloor heating system, which looks like this. And essentially you pump hot water in one, heats up the floor and comes out there. That's a lot of work, especially if you're going to retrofit it. So if you're building a new building or completely renovating a room, this makes a lot of sense. This has to go under the concrete, under the tiles. But if you're retrofitting a room with a wooden floor, this doesn't make a lot of sense. So what we've decided to do is a more American system. And that's where in the roof here, we're going to have like a box. And inside the box, we're going to have a heat exchanger. And this is just basically like a car radiator, a bunch of copper pipes. And what you do is you take some of this hot water. Let's say you pump it up here, and then take the cold water out here. So you pump it in the hot water here. It goes through this heat exchanger, which is like a kind of coil, heats it up, and then the cooler water is returned here. And essentially all you do is you have a big fan here, some kind of housing, and this fan blows air across this heat exchanger. So the theory is you take your hot air from the hallway. Let's say this is a hallway. We'll just pretend it's a really long hallway. We take the air from the hallway. You suck it from the hallway using this fan. You heat it to the temperature that you want, and then you can, let's say, and then you can push it into the bedroom. Let's say this is a bedroom here. So in theory, this is all good. And basically the flow of the air is going to be, it's going to go through the fan here. It's going to get heated up and it's going to come into the bedroom, come out these vents. And these vents are designed to actually like push the air across the ceiling to spread it out across the whole room and then down the walls. And then the way it gets back here is when you have a door, inevitably there's some gaps, under and around the door. So the air is kind of going to go under here into the hallway and then back up into the return. If you want, you can also add, strategic. You try and place the return vent on the floor if you're trying to heat, or if you're trying to cool, you'd want to vent higher up because the hot air is going to be sitting at the top of the room, so you want to push that out. But when it's cold, the cold air is going to be sitting on the floor, so you want to push out the cold air, replace it with hot air at the top. And another advantage of this system is if you've got allergies or hay fever or anything like that, it's very easy to install a filter here, basically just like an air filter. And then all of the air that's coming through has to pass through this filter. And it's possible to filter out pollen, smoke, odors, whatever you want. So a big advantage of this system is you get control of the air quality inside your house. And there's a lot of research that's coming out that indicates that air quality is quite important, especially for things like asthma and developing allergies as well. So it's just one of the advantages. Another is all of the walls of the room are free. They don't have a radiator, and you don't have to dig up the whole floor. So the downside, of course, is it takes up all this space in the attic here. But we have quite a big attic and quite a lot of rooms, probably more space than we really need. So for us, this isn't a huge concern. And I quite like the idea of having a utility room here. And now in the US, it's very popular to have air conditioning in residential houses, much less common here in Europe. But if you wanted to do that, all you would do is, say at this point here, you'd put in an AC evaporator unit. And this basically would cool the air. So if you wanted to, in the future, you would just splice this duct here, put in a cooler or a dehumidifier or anything like that, basically operate on the same principle. You could add more filters. You could do plenty of stuff. So it's pretty customizable and future-proof. And one thing to do is, obviously, this is just circulating the air around the house. If you have a really sealed house, this isn't good enough because you're going to be breathing carbon dioxide and stuff, and you're not going to be getting any fresh air at all. In our house, that's not so much of a concern because everything's quite leaky, but just in case you want to do that, all you have to do is you have a duct here with a valve, and this is your fresh air intake, and this is just a controllable valve. They call it a damper when we're talking about air ducts, but essentially you can open and close this and let more or less fresh air in. And as for air getting out, well, if this is a bathroom here, typically in bathroom you'd have an extractor fan like this with a fan in there. And this is constantly going to be, normally all the time, it's pulling some air out. And then some trigger, like maybe it's a humidistat on the wall, or it could even be an odor sensor on the wall, or more common, it's just a timer attached to the light in the room. But this triggers the fan to go from low mode to high mode and suck more air out. And just like before, generally this is just pulling air underneath the doors and through the leaky passages. So in theory, fresh air is going to be coming in. It's always going to go through this filter. It's going to be pumped into the bedrooms. And then dirty, humid air is going to be extracted out of the bathrooms like that. So in theory, you buy all this kit, and you buy all this kit, and then you just join the hot water pipe to here and the cold water pipe to here. And then the job's done. But as you can see, I've left a lot of white space, so that's not the case. So the trouble with that is this stove, it contains about 30 liters of water, and it's about 30 kilowatts. So it's not going to take it very long at all to heat this up from the recommended. So we're trying to keep it at between 60 degrees and 80 degrees. So that it should come on if it reaches 59 and turn off if it reaches 81. But it's not going to take it very long at all to do that, let's say minutes. And once it does that, it's going to turn off again. And then we might use that up to heat the house, and then it's going to turn on again. And this rapid cycling is not good for these stoves. So one, you've got this electric element which has to constantly be heating and reheating these pellets. And also the stove doesn't get hot enough, the interior, the metal parts of the stove don't get hot enough to burn the pellets efficiently. So you end up with more carbon and soot, which means you've got to clean them more often, and it's worse for the environment. So the way around that is you just put in a whopping big storage tank. So I'm going to draw a big storage tank here. And essentially what you do then, you connect this is, in our case, this is 500 liters. So the stove is going to heat up this whole 500 liters. It creates an energy store of hot water, and then you just take the hot and cold supply from this tank itself. Now, unfortunately, the theory is simple, but the reality is complicated. So actually, these are just connected like this, and these are just connected like that. But there's extra hardware along the way. So this works very similar to the stove in that you'd have a level of hot water here sitting at the bottom. And then in theory, you'd have some hot water at the top. So basically we want to be taking cold water, heating it up and putting it in the top. But from here, we want to be taking the hot water from the top and then returning it to the bottom. And then this gives the stove a chance. And you can place, you can place a thermostat here, here, and here, and you kind of keep an eye on how much energy is stored in the tank. And there's some electronic control units that monitor that and then decide when the stove comes on. So obviously the first one thing that we need here, water isn't going to magically just flow around here unless this were much higher than this, which is not. And so we've got to put in a pump. So this is my representation of a pump, and this is going to be pushing the water this way. Now, before the pump, the stove is made of steel, this thing is made of steel, the copper pipes are made of copper, and some of the fittings are brass, but you get a bunch of debris and like sediment and stuff that accumulates in these pipes from the water just sitting in there and corroding the metal, and remains from the soldering process and all sorts. So it's quite normal to put in a filter here. Essentially in here there's a big magnet and there's also a strainer, and then it has a thing on the bottom with a tap which goes to a drain. And all this means is that all of the water that's coming through here, it's passing through this filter, it's going over this magnet. Any iron containing bits are going to get stuck to the magnet, and then you kind of ensure that the whole circuit is free of bits of metal and sludge and stuff which will accumulate here at the bottom, and then you just service this regularly. And it's not a problem. Another issue is that you can't just put 10-degree water in the bottom here and expect it to come out at the top at 80 degrees. The stove actually, if you did that, you'd get a bunch of like carbon buildup and like oils and tars and stuff accumulating on these cold surfaces in the stove. And so the stove manufacturer actually mandates that the minimum supply here has to be at least 50 degrees, which is below the 60 degrees. But when you're starting up and when you're cycling, this is always going to be a problem. So what we have to do, we have to put in a valve here. And this is an anti-condensation valve. And all this does is it joins up with here. Now, if the water coming through here is above 50 degrees, it just takes it straight from here. So, the cycle is going like this. It's not a problem. But if the water is less than 50 degrees, or I think 55 degrees in the one that I've chosen, what it does is it starts taking it from here. And this creates a much smaller circuit. So essentially, when it's cold, it's 10 degrees. Initially, it's going to be 10 degrees. There's no getting around that. But there's only a small amount of water in this circuit. And so it's going to heat up quite quickly. And then as it reaches 55 degrees, it's going to start opening and drawing water from this cold tank. Not all at once, but just a bit at a time, until the whole thing is 55 degrees. And then all of the water is going to be going through this circuit, and this will be completely closed off. So that piece of hardware is quite important. Another factor to consider is as the water is going between, let's say, 10 degrees and 80 degrees, it expands. And if you don't leave anywhere for this expansion to go, it will crack a joint in a pipe or a fitting, or even worse, something like the storage tank or even your boiler. So the way to get around that, well, there's two ways. One is that you could have a big tank in the loft, which is just open to the air, and as it expands, it gets fuller, and as it gets cooler, the tank at the top will get less empty, and you keep it supplied to some minimum level. But then you've got a big tank of cold water sitting in the loft, pretty much open to the air. It's not very hygienic, and most modern systems don't include that. Most modern systems, they just pressurize the whole system from the mains, and then they have an expansion tank. So that's what we're going to do. We're going to put in a big expansion tank here, and this is basically just a smaller tank here, but inside it has this rubber balloon connected to an air valve on the top, just like on a car tire. And essentially what happens is you set the balloon when the whole system is depressurized, you set it to a certain pressure, and it goes to a certain size. And when the water expands and increases the pressure here, it squeezes this balloon and makes it smaller here. And what that means is that all of this space between the original size of the balloon and the new size of the balloon, which I've shown dotted there, is available for the water to take up. And this basically keeps the pressure of the system between 2.5 or between 2 and 3 bars. So it is important to have a safety valve, and somewhere on the top, I'm going to put it on the top here, we basically have a little spring valve, and this is set at 3 bar. And this means that if the pressure ever, for whatever reason, let's say it goes up to 95 degrees, it's going to start dumping water out of here so that nothing else gets damaged. So this is a protective unit, and pretty much every system, or in fact every system, should have one of them. At the moment, ours does not. So you get a lot of sputtering and pressure fluctuations within the system. And lastly, if the boiler were to, say, malfunction, let's say it dumps a load of pellets in here, and then there's a power cut, and the circulation's not running anymore, so it's just heating up this water, and this gets to 95, 98, 99 degrees. It's about to become a steam generator, which is not what the system was designed for, and the pressure's about to probably exceed safe limits. So what we do in this situation is we're going to put in a strange looking valve. Looks a bit like this. And it has a temperature sensor which goes somewhere where the hot water is. And effectively, normally this is just open and it's just allowing water to pass through the circuit like nothing's happening. But if the water here gets to 95 degrees, this closes this and dumps the water here into a drain. The hot water goes straight out into a drain. Now that would depressurize the whole system. So you also have a cold water supply that's coming in, and then you join that up to here. So in the event that this reaches 99 degrees, this is going to start dumping hot water and pumping in cold water into the bottom, into the furnace here. Sorry, into the boiler. And this should cool the boiler down. And this is just a safety device to prevent an overheat from ruining the system. So how do we join these up? Pretty simple. You just connect the hot somewhere here and the cold somewhere there. But there is a device in the middle that looks something like this. And effectively, we're going to, let's say it looks like this. We join this up to this valve, and then we take this one to the hot here, and then the cold, we're going to take, it goes behind, we're going to go in here somewhere. So this is still hot, this is still cold. And what this valve looks like, if we actually draw it, basically a big circle in here, and it's got like tube that looks like this. So in normal use, it's basically just allowing this cold to join up with here. So the hot water is going to come in, it's going to go through this path here, up to the hot, down, and cold water is going to go through this path here to the cold. But what it can do is you can adjust it and you can turn it, and it will actually mix some of it. So sometimes it will take some of this cold water here, will make its way back into a circular unit, and it achieves this by basically just moving this way, turning this ball in the valve here, turning it this way. And it will mix it. And the geometry is a bit more complicated than that, but essentially that's what's going to happen. So Basically, we can also control, this doesn't always have to be 80 degrees, which might be a bit too hot, and that might be hotter than we want the air to come out here. So we can kind of control the temperature of the water in this circuit up here using this valve. Now, at the moment, this is manual, but later I'll probably upgrade this and make it some kind of automatic controlled valve. And then lastly, the actual hot water. So we've discussed how you can heat it. And if you were to do underfloor heating, let's say we wanted to do that downstairs, it would be quite simple. You just basically connect these up to this circuit, and they might need a separate pump, operate at different pressures, but the principle is there. It doesn't stop you from doing that. You could add radiators or whatever if you want in the future. And then finally, for the hot water, inside here, there's actually a separate coil made of stainless steel. Now this goes around like this inside the tank. It's quite long, and you put cold fresh water in here. This is drinking water, and this will go through these pipes, which are all ribbed, so they're textured to increase the surface area. And as it goes through, it's getting hot, and it will come out here. So this is your hot water supply, and you just run this along the house. Let's say you have a tap. This is the last hot tap in the house, and then along the way, you've got a bunch of other hot taps being taken off. So it might be like kitchen, bathroom 2. Bathroom 3, and then finally the shower head, let's say, which might be the furthest away point in the house. So actually, let's make this a bath. So this might be the hot tap in the bath. Now, if you've got quite a big house, this run can be quite long, can be tens of meters. And when you turn on the tap, you're waiting for hot water, and the water that's hot has to pass all the way around the house, many tens of meters in a copper pipe, often uninsulated, and then finally heats up. So it wastes quite a lot of water, and it wastes quite a lot of hot water, because in that process, all of the volume of water in this pipe, you basically just wasted and replaced with cold water in here. Now, most of these taps, they also have a cold water supply. So we would have, let's say we have our main cold water coming in here. Oops. And this would also actually be connected to this. So normally when you run the mixer tab, you get hot water and cold water. So this is the cold water coming in and the hot water here. Now, one thing you can do to get around this problem of waiting for the hot water to get hot is, as you're running this pipe around the house, you just run another pipe in parallel to it. And then at the very end of the circuit, you put in a pump. And at the very end of the circuit, you can turn on this pump and you force the hot water, which is already at high pressure at this end of the pipe, back down this pipe, and you join it up here into the beginning of the hot water circuit, just before it enters the tank here. And then you put in some non-return valve here to stop it contaminating your cold water supply potentially. Now, the issue with this is, what this does is, when this is on, it's constantly circulating water around this. So it means that the water here is always hot, because it's always moving around. It doesn't really, as it's cooling down, it eventually just gets pumped back. But you don't want this to waste loads of energy, so you put it on a timer here. And you put this on in the morning and in the evening when you want to take showers, or when you're going to be using the taps. And this is called a hot water return. It's not very common in Europe, but in a big cold house, it's probably a good thing to do. And if you're putting all the plumbing in anyway, this pipe can be a lot smaller than this pipe, because it doesn't have to carry that much volume of water. So it kind of makes sense, if you're doing a complete renovation, just to run this extra pipe. Maybe it's like 8 mil, just to run this extra pipe as you're doing it, and then you can choose to put this in at the end later or not. So this is the total system. We've got our hot water for bathing, which is drinking safe. And all of this hot water, which is not drinking safe, is in a completely separate circuit. And these two never touch, because this is just a stainless steel coil here. And it's important to note that you have to put inhibitor inside this water, and this stops the whole thing from rusting, because this tank is steel, the boiler is iron, and lots of the other parts. So basically you put in, I don't know how many it is, 5 liters or something of inhibitor, and it stops everything from rusting. So the advantages of this. So this type of air system, heating it this way. So the advantage is, obviously you can control the temperature, and that's easy to do. To control the temperature, you just control the airflow or the hot water temperature. And if you want, in the room, you can put in a little thermostat and a valve or a damper here, which is linked. And you could do this for every room. So each room, you can just get more or less air depending on what this thermostat is doing. So if it's too hot in your room, or if your guest wants a warmer room than you, then this will open and they'll get more airflow than you will. You can also use this to measure things like the CO2 level in the room. And again, you would just increase airflow. Or you could increase if you're measuring the CO2 at this point over here, you might want to increase the airflow through the fresh air, like replace more air in the house, more of the stale air with fresh air. So then you can do the fresh air intake. You can also measure the humidity. And this, just like you do in the bathroom where the fan senses the humidity and turns on, you can do that in the other rooms as well. And you can either increase airflow. If it's like local humidity in one room, like you're sleeping in there, for example, you can take more fresh air. Or you could actually turn on the AC or dehumidifier. Now, in principle, AC and dehumidifiers are the same thing. You'd put a cooling coil in there, and then this also has a tray to collect any condensate, all the water that drips off. That's got to go somewhere. You can't just let that drip onto the floor. Then you have that built in. And then finally, particulates. You can change the filters, and you can control that with the airflow and the fresh air intake. And all of the fresh air that's coming in here is going to be going through these filters. And these filters can actually filter out pollen and mold spores. You can go down as low as you want, so long as your fan can generate enough, handle the pressure difference across these filters. So the finer filter you get when you want to start filtering out things like smoke particles or viruses or something, you need a really powerful fan. And these are actually quite expensive. Fans that are powerful enough to cope with these types of filters and this type of system, but also quiet enough to be directly overhead of potentially a bedroom, those actually run into many hundreds of euros. So it's not a small investment. It's not like an extractor fan where the whole kit is 100 euros. These are actually quite expensive. So we've already talked about, so these are the advantages of doing a system like that as opposed to radiators, which just trap dust behind them and take up space on the wall. And underfloor heating is also possible, but requires a lot more work. So this is basically a summary of the system. And the reasons we like it is the pellets are sustainable, at least in theory. I think in practice as well, they're sustainable. And if this doesn't work or pellets no longer become available or whatever, you can just take this door off and burn regular logs in there as well, or coal or anything you want. And we do have quite a few trees, so in this case, when you want to run it manually, you would just go in the morning, light the fire, turn the circulator on, heat up the whole system, and then let it go out. And that's how it works. So this is a summary of the system. At the moment, I'm struggling to install this and connect these two together. But as it stands, I've purchased all of the hardware for this side of the circuit. And, well, actually up to here, probably. This is about where I've purchased. And then this will be topic of another video. So it's been quite a long one. It's taken me quite a long time to go through that. But potentially someone out there finds this interesting. All right.